Okay, in this video, we're going to focus on the use of the velocity time graph as a problem-solving tool. So we have a simple situation here. A car moving 15 meters per second sees a person who has fallen down in a crosswalk 30 meters ahead, and the car takes about 3 seconds to come to a stop. So let's practice representing this situation with a motion diagram also. So here's the car at various moments of time. It's slowing down, and eventually it comes to a stop. Now, what we don't know, here's my velocity vectors for that. And I'll leave the velocity vector off completely there because there's where it comes to a stop. Now, what we don't know is the person here, or is the person, for example, there? In other words, does the car hit the person or not? Well, we hope they won't. But we're going to find out. We know the person, wherever they are, is 30 meters ahead of where the car is. So let's take a look at whether the car actually takes less than 30 meters, exactly 30 meters, or more than 30 meters to come to a stop. And that way we'll know if the person's safe or not. Now, there's probably lots of ways to go about this particular problem, but I'm going to focus, and I want you to focus on building equations from graphs and using those equations to solve problems. So those graphs is a basis for solving problems. So here's the velocity time graph for this situation. There's time, there's velocity. These will be in seconds, and these will be in meters per second for velocity. Now, it starts out moving really fast, 15 meters per second. Eventually, it comes to a stop. And we are going to assume a linear rate of decrease of the velocity. In fact, we will assume that in many, if not most, if not all situations, we will assume that the rate of change of velocity will be linear. All right. Now, this spot up here is 15 meters per second, and that's a time of 3 seconds. So let's see. What can we say about this, the motion by way of this graph? Well, we can write the equation for the area, because as you read about the other day and as you watched in the video, the area is equal to the displacement. Now, let's label this point A and this point B where they come to a stop. Then we can say the area from A to B will be equal to 1/2 of the base times the height. This is a triangle, so 1/2 the base times the height. The base is time, and that's the time from A to B. And the height is the velocity. Base times height is the velocity at A. Point A, it's going 15 meters per second. Now, all the things I'm showing you here are the kind of steps that I would like to see as you are problem solving and presenting those problems to me. Okay, so now that we have the equation of that area listed off, we're going to go ahead and we're going to gather all of our information in a table. I call this a list of variables, and you'll love making these. So we have the velocity at A, velocity at B, that's 15 meters per second, that's 0. We have the displacement from A to B, and that we don't know. We don't know if it's more or less than 30 meters. And then we have the time from A to B, and that's 3 seconds. Now, eventually, we'll expand this to include acceleration, and then we'll be able to actually make the area of the line, the equation for the line and the area, both of those. But now we're just with the area. Now, why is that a helpful thing? Well, if we look at our list of variables, the thing that we don't know that we really want to know is how much distance does it take the car to come to a stop. So this is our target variable, and it appears right there. And conveniently enough, we know VA and TA to B, and so we actually have everything we know to solve this question. This is 3 seconds, and this is 15 meters per second. And so when you math that all out, you get 22.5 meters per second as our displacement. And in fact, yay, the person is safe. They're 30 meters away. from the car when the car sees them. The car only takes 22.5 meters, 22.5 meters to stop. All right. Now, some of you may have looked at this and said real quickly, the person's going to get hit for sure because I can just take 15 times 3 is 45. They're going to go 45 meters. That person's dead. So a quick thinking about that, this assumes that it's always going 15 meters per second, but it's not. In fact, except for the very first instant, all the rest of the time it's going less than that. So really that thinking doesn't work. It's one of the reasons I like this graphical approach. It's new for many of you, I will think. You know how to do the math, but thinking about it as a problem-solving tool might be new. But the other thing is you're not very likely to make mistakes. Now, there's another approach to this problem, which is to use the average velocity concept. The average velocity is equal to delta x, whoops, a few too many deltas there, a to b over the time from a to b. And this is the average velocity over the stretch from a to b. By the way, why subscript? Why bother putting those in? There's only 2 points. What if there's 3 or 4, which we'll do questions like that? Then it's good to be able to distinguish, is that the average velocity from A to B or from B to C? So that's why I do that. Now, the approach to solving the problem this way requires that you realize that when the change in velocity is linear, so when delta V linear, then the average velocity equals the average of the velocities. Otherwise, it's not true. But this is linear, so it is true. In a sense, what it's saying is it spends the exact same amount of time at every velocity. So what we're going to do is take the velocity at point A plus the velocity at point B and divide by 2. That's just taking the average. And now I'm going to come down here because I ran out of room. Delta x from A to B over the 3 seconds will be equal to 15 plus 0 over 2. Again, just taking the average. And if you math that all out, you get 22.5 meters again. All right. So what we see here is a couple of things. One, that you got to be careful in thinking about what's actually going on. It's super easy to multiply some numbers together. It's a whole nother thing to make sure that that actually makes sense. 2, using graphs to create equations to solve problems. And 3, the problem can be used with the definition of average velocity. But for upcoming homework assignments, I'm going to have you stick to this approach for the reason that you're less comfortable with it. And it's good to have some tools in your toolbox that you know how to use, even if they're not ones that come easy to you to begin with. So that is a video on using velocity time graphs to solve problems.